Greetings, Alex here again. Now, this may seem a little bit off topic for people that watch this channel regularly, but is anything really off topic here? If you've never seen my channel before, welcome. It may be a little bit of a drink from the fire hose. Open wide! If you're coming here as just like a sparkly-eyed gamer who wants some information on their favorite Switch, or if their mouse is broken and looking for some problems. So, what I do here is usually extremely nerdy. If it's particularly nerdy, I will tag it as such. This video, I'm going to try to keep on the meh nerdy level. And if there's enough interest, I could go into excruciating detail about everything that I've talked about. But I think this will be sufficient for at least getting the point across. And what is that point, you may ask? Well, you're going to have to find out. But what inspired this video was that the left mouse button on my mouse went bad, as they do. Eventually, they're all going to die. But I've gotten pretty good at replacing these over the years, and I got my first electronics kit in the 80s. I spent a couple years working on fabricating industrial control enclosures. I also do a lot of electronics hobby stuff, so, you know, mice are kind of tinker toys. It's not that big a deal. These particular switches all fail roughly around the same time in roughly the same way. So this is a repeatable problem, and things that kind of goad me on to do things are when there's a lot of misinformation or gaps in knowledge out there, and there's a whole lot of hubbub and hoodoo and voodoo going on with a lot of things in the gamer world, and that has to do not just with the fact that people just like to jump on forums and say things to sound smart, but manufacturers have been particularly misleading because it's been a very lucrative area for the last, 10 years or so. And it's reached that point to where you're like, the guys in the suits and ties have gotten their claws into it, and now I just can't believe anything. And I think a healthy dose of skepticism is usually good. So let's talk about the problem. We'll talk about the situation surrounding it. We'll talk about the mechanics of everything involved. We'll talk about possible solutions. We'll talk about things that do and do not work. And then we'll talk about where to go from there. So with no further ado, the video. So like I said, this is a problem with my Logitech G502 switches, but it also applies to a lot of the newer Logitech mice and other mice as well, like this Pro that uses a 50 million bajillion switch version. And if you spend any time online, you know that this has been a virtual plague of problems with these. I'm pretty happy with the G502, but it's just the latest in my line of various mice. So I have a whole lot lying around to work with in terms of, comparing mice and switches and that type of thing, as well as this just being a graveyard of ancient computer technology in general, to like old bizarre 90s abominations to like new bizarre 21st century abominations, and a metric crap ton of partially disassembled mice. But ironically, this G502 is the only one that I actually bought in a store because I am a dumpster diving, thrift store, and Craigslist and maniac. So the way it usually works is like little Timmy or Janie gets a new gaming mouse for Christmas, and then they try playing Dark Souls for like 2 months before they decide that, well, hard things are hard, and they go back to playing Minecraft on their phone or whatever. Then their parents dump the barely used computer mouse off at the thrift store, and I buy it for $5. But anyway, the actual problem we're talking about is with these little Omron switches, specifically the D2FCF series, that are much beloved by the community and used in a lot of Logitech mice. So I'm going to tackle this scientifically. We're going to define the problem, brainstorm solutions, present options, summarize the results, and then suggest actions. So if you're playing along at home, kids, just remember with this wonderful acronym, DBUPS. All right, that was a cringy joke, screw it. What we're going to do first here is define the problem. So what exactly is going on here? So if you read the title, you know that this is the double click problem or the click and drag problem. And it kind of manifests when you try to click something and it accidentally clicks twice in rapid succession, or you try to drag something and you just can't drag it. So you can use a mouse events page right here, and you can see how it's registering several clicks, and then click and drag is pretty obvious. When you try to drag something across the screen, it just kind of like drops it or stutters, like trying to select a group of files and drag it into a folder or something like that. And it's annoying to gamers because say you're on a window where you're, selecting some kind of specifications for your leveling up, and you accidentally double click on something and can't undo it. That sucks. Or when you're innocently prospecting for gas and somebody decides to freaking Zerg rush you and you can't drag select units and assign them and send him back to the cockroach hell like the cheesing little noob that he is. On to point number 2, brainstorming solutions. Now, you would think, hey, why don't you just go ahead and use a more rugged switch, something that's stronger and built for more cycles? After all, we have the 50 million zillion billion click versions of the Omrons now, right? Wrong. Wrong. After all, that's what Logitech did, and it just made the problem even worse. This was never about improving the product. It was about having a unique selling point, about increasing perceived value, and about feeding off of the hype. As the Omron internal documents say, it's a trend, ride the wave, blah, 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 and all that kind of nonsense. So you're probably thinking, well, what do you mean? 50 million is more than 10 million or 20 million or 5 million. Well, thank you, hypothetical person, for transitioning us into the first problem. Specs are a lie. Now, lie is a little bit harsh, but specs are misleading or misapplied purposely by the guys in the suits and the ties in the marketing department, and the specs don't always apply in our use case, and I'll talk about why that is in a little bit. Our use case right now being gaming. And this video is not about those 50 million click models, but just avoid them, take my word for it, it's a trap. And if you have them and they're working great for you, don't blast me in the comments. Great, enjoy your mouse. So I won't talk yet about the specific cycle life of these switches, but let's talk about the specifications of this series of switch, as laid out in Omron's test documentation. This is where the goofy stuff stops and we start getting nerdy, so strap in. These are the test conditions and specifications of the DF2 series mice. They're tested at 5 and 6 volts DC at 100 milliamps and 1 milliamp. That's going to become extremely important later. They're held at 65% humidity, and the tolerance for the series is plus or minus 20% of spec. So if they don't meet that, they're gone. Contact resistance is 4 times spec. So bear that in mind as well. The regular switches, the unmarked one, are rated for million cycles, and that is at 120 presses per minute, i.e. 2 presses per second mechanical. So according to Omron, they are guaranteed no electrical mechanical defect exceeding 20% or minus 20% of the specified value, or 4 times the initial value of the contact resistance. And that is across the entire prescribed cycle, 5 million in this case. They guarantee that as long as you are using them how they prescribe in the datasheet. More on that later. The electrical ratings are done at 30 operations a minute, i.e. 1 click every other second. So what they're rating them at really depends on the test that they're presenting, so it's a little bit you have to keep in mind. And this is where, if you're a logical person, the warning bell should be going off in your head, because with those super hyped new switches, they're claiming 50 million cycles, and if they're rating that electrically, that's at 30 presses per minute. So if you do a little bit of simple arithmetic, we find out that that is 3.17 years that they claim to test these. Even if we divide that by 4 for 120 cycles a minute, that's still 9 months. We're not having a baby here, we're testing a switch. And that leads us to the second part about the specs don't equal our use case, in addition to them to being misapplied, because they're more than willing to say 50 million cycles is a quoted spec without telling you about the other specs. And according to their very own data sheets, gaming exceeds the max cycle frequency, the max over travel, unless you're very accurate or your mouse is designed around that, the maximum pressure, the maximum speed, and the full release, as in taking your finger completely off the actuator between every click. So gaming does violate this, and therefore it violates their performance guarantee, i.e. the specs aren't guaranteed, and it even violates the warranty. And in their very sheets, they say that performance is not guaranteed if any of the conditions are exceeded, and the warranty is void if any of the conditions are exceeded. Also, if you read into the fine print a little bit more, you'll see that compound specs are not guaranteed. For example, in isolation, you will meet the spec for voltage or humidity or something like that, but when put together, if you're looking for running at the maximum voltage at the maximum humidity, those two put together are not both guaranteed. So that's why at the beginning I said specs are a lie, because they're cherry-picked and misapplied just as marketing hype. Now, there are various unhyped places that you can go and check out the actual reliability data of actual electronic components, and you can view the standards for electrical lifespan, as well as like testing methods and predictability as far as like how long you can properly expect it to live. But basically, those tests aren't clicked for 3.17 years to get to 60 cycle life. They are predicted based on a model and basic evidence. But we can't blame the switch manufacturer and the marketing people in all cases, because the people that are speccing these, the engineers that are putting these mice together, are by their very nature violating the specs. Here is probably the most important point when we're talking about why this plague is happening. If you recall, the datasheet said the minimum electrical conditions for this series of switch was 5 volts DC at 100 milliamps, while some of the tests were carried out at 6 volts DC at 1 milliamp. And that's not within specification for the particular series of switch that we're talking about here. And that seems like a fundamental, elementary, like freshman level mistake, so why is it that they do that? And there's a couple answers, but one of them is that it's always worked in the past. They've used these switches for years. So if it used to work and these new series of switches are better, therefore these new series of switches should work better. But that's not always the case, and I'll show you why. And the second reason is that they'll use an unappropriate part because it's considered to be desirable by the customer. People have an attachment to these switches from back in the day, so they put the cart before the horse in terms of weighting marketing against research and development of their existing products. But the fact remains that it's the wrong part for the job. But they used to work fine. That's very true. So what has it happened between them and now that caused this plague of failures? Plague of Failure would be a great goth band name, by the way. Well, fortunately, it pissed me off enough that a little bit of digging, and now is where we get into the crux of the issue. So here we go. Remember, I said it doesn't meet the minimum specifications. We're used to exceeding maximum specifications where you blow things up. Not meeting the minimum spec doesn't really register. Well, if we're not running enough current and voltage through a switch for it to operate properly, what we're basically saying is that we don't have enough wetting current. Because unless you're in a perfectly dry, vacuum-sealed, rare gas environment, you're going to have some kind of subtle oxidation on a switch, especially one that sits in a no-contact state like the switches on these mice. Different conditions require different form factors, different construction, and different materials used, and the way that you use them. And look, Omron knows this. This isn't their fault that these switches are quote-unquote going bad. They even provide this nice handy little chart in the datasheet to show you what loads are appropriate. But the loads that we are talking about are called microloads, or if you prefer, microcurrents, like under a milliamp. And we're going to refer back to this chart a few times, so get used to seeing it. There are two series of switch right here, the D2F01 and the regular D2F. One is for microloads and one is a general load model. The D2FCF series, no matter what the cycle rating, fall into the general switch series, not the microload series. And their minimum guaranteed operating point is 100 milliamps at 5 volts. But we're nowhere near that red arrow, and we're not even in the happy operating range right here. We're way down in the lower left there be dragons range. And these new mice violate the minimum current and the minimum voltage requirements. So I dug up a couple blasts from the past to illustrate why this kind of worked with the older mice and it doesn't now. This is an MX400 mouse that has these switches in it, and this is the venerable and much beloved MX518 gaming mouse that kind of put these switches on the map and built up the hype that made them want to continue putting them in the newer models. So we can break the difference down into minimum voltage and current for number one, and number two, bounce, chatter, and polling rate. Those are two big differences between these. Now all these mice work about the same. There's a laser that does the tracking, there's a microcontroller that sends the signals out to the USB, does all the math, and controls the logic for all the switching. Now the MX400, that used this particular controller right here that was an application-specific controller, 8 bits, and it was used for making mice. The MX518 used a slightly fancier schmancier chip that is, the datasheet is right here, that was the CY7C63743 numbers. But a lot of these modern mice that are having these problems have switched to much faster processors like these 32-bit ARM STM32 chips. They're not application specific to mice, they're general purpose processors, so let's talk a little bit about them. Nerd warning number 2, we're taking it up another notch here. So what we're talking about is, back in the day, logic voltage used to be generally accepted at like 5 volts. It can be 12 volts, it can be 24 volts or something like that. But as we're moving on through the years, that logic voltage standard is getting lower and lower as we're moving to lower power and portable devices and things like that. For example, if you want to run off of a lithium-ion battery or something like that, those put out 3.6 volts, so it's much more difficult to use a 5-volt logic because you're going to have to boost that voltage in there with like a switch mode DC to DC power supply, whereas you can just run a 3.3 volt logic chip directly off of that battery. So as the market is running toward that, everything that's coming out is going to be more 3.3 volts than it is 5, and it's even moving down to like 1.8 volts or 0.9 volts depending on the application. So that's why we see that paradigm shift there. So where it used to be higher current and higher voltage, now we're moving to both lower voltage and lower current at the same time because of power consumption and because of just the changing paradigm of the logic levels. Now bear in mind, we're talking about hitting the minimum specified levels required to make these switches work right and consistently. And looking at STM's data sheets, we can see that it'll sink at least 8 milliamps out of a general purpose I/O pin. I hear you saying right now, all right, Alex, you lost me. So let's talk about how this works. We have a microcontroller and we have a switch. It's usually off, then when we push it, it's on. That sends a signal to the microcontroller by giving it a particular voltage level. It doesn't care about the switch. The switch is turning on a voltage, which used to be 5 volts DC, and that signals to the processor that a button has been clicked. Now that has a limiting resistor, usually in the range of 1 to 10K, and sometimes it's application specific, like 1.5K for USB or 4.7K for serial. Generally, it'll be in the range of 4.7 to 10K, sometimes lower, sometimes higher, and smaller means more current. And this is nothing obscure and arcane. This is well known, and you can just look in the data sheets to see what the proper procedures are and best practices. And let me remind you right now that we are talking in our chart about two different models, the general model and the model that is specifically made for microloads, i.e. the D2F models and the D2F01 models. One has a minimum load of 100 milliamps at 5 volts and the other at 1 milliamp at 5 volts. So those are the targets to keep in mind, and since I love you all so much, I took apart some of these mice and ran some tests myself. And these were my results. As you can see, the MX400 was pulling 0.62 milliamps at 4.95 volts. The MX518 was pulling 0.36 milliamps at 4.97 volts, and my G502 was pulling less than 1/10 of 1 milliamp at 3.62 volts. That means that for the minimum spec of switch in this series, in terms of hitting our current and our voltage target, the MX400 hit the voltage target and almost hit the current target. The 518 didn't quite hit the current target as well, but it did still nail the voltage target. The G502, that didn't hit either. It was nowhere close. So you can see this gradual progression away from the specs and into unknown territory. So we've just kind of creeped from borderline to, well, that was the straw that broke the camel's back, and now we're on the other side of the fence where we can't guarantee lifespan or reliability. In other words, the G502 is way out in the weeds here. And this is not new tech. All of this has been known going all the way back to 1933, 1934. But what we have here is a case of saying if it ain't broke, don't fix it over and over again until eventually the problems pile up underneath you and bite you in the butt for not doing your homework. But fear not, for this jerk right here has done your homework for you. So let's talk about that current. Because now we're going to discuss one of my favorite things to rant and rave about, Ohm's Law. And this is the part we care about right now. So in our case, current equals voltage divided by resistance. And in our series of switches, we're talking about a current of 1 milliamp for the one series or 100 milliamps for the other series, but we're never going to hit 100 milliamps without blowing our chip out, so we're focused on the 1 milliamp right now. So looking at our equation, higher voltage or lower impedance or resistance is going to give you higher current. So if we have our microcontroller right here and our mouse switch right here, and that's going to feed our logic signal in, then we're going to take this resistor and suck current through the voltage power supply when we toggle the switch on, depending on the values of R and V, or the resistor and the voltage. But if we look at this kind of like boilerplate schematic for a mouse that I flashed up earlier, you see that we don't have any pull-up resistors. We just have these switch buttons that are connected directly to the microprocessor. That's because they're using the internal pull-up resistors that are in that processor instead of external resistors where you can control the value of them. That means you're stuck at whatever value is spec'd in the microprocessor. And usually that's a range, but in the MX400 chip, the older chip, the range is between 4 kiloohms and 12 kiloohms. I actually measured mine at 8 kiloohms. And in the slightly newer chip that was used in the MX518, that range increases to 8 kiloohms to 24 kiloohms. I actually measured mine right around 14 kiloohms, a little bit more. And both of those chicks run off of 5-volt logic, not the 3.3 volt logic that our STM32 chip runs off of. The pull-up resistors on a variation of that board that I just showed in the last picture are 1 kiloohm, which pulls 3.3 milliamps of current through the switch on those boards. But we are not running on 5-volt logic here. We are running on a 32-bit 3.3 volt logic chip, which is between 1.3 and 1.6 usually, and we're not using external pull-up resistors. So this is a diagram of the internal pull-up resistor right here. Now they give a range on the data sheet of 30K to 60K. Usually they just say 40K to make it easy. I actually measured the one on my mouse, which is the L100 series, at 41.3 kiloohm. And I measured the voltage at the IC's terminal at 3.22 volts. So back to Ohm's law. These calculators online are real convenient. If we put in 3.3 volts at 40 kiloohms, we see that our current is 0.08 milliamps, which is way, way low. Conversely, if we use the older values of 5 volts and a resistance of 4.7 k ohms, then we have just about right around a milliamp, which is good for our low power switch. And again, Omron knows this. They put an entire section on microloads in the datasheet of this series of switches. So that just means that both the datasheets and science show that, well, wrong. There's a thing called a bathtub curve when you're talking about components. That means that there's expected failure rates at the beginning from manufacturing tolerances. Then at the beginning, you're supposed to have your useful life where you don't expect any failures. And eventually at the end, you have wear out failures. But this middle part, the sweet zone where we're supposed to get our 50 million clicks, doesn't exist anymore except in perfect circumstances because we're way too far out of spec. The bean counters read the comments, they know what the kiddies like. And in terms of sales dollars, sentiment about a particular switch equals money, even if what they're using is wrong. And that's kind of landed all of this in this realm of, well, you know. But again, this was okay-ish with our old mice until we lowered the operating voltage and lowered the current. Also, there's a second dimension to this. We raised the speed and, as another value add feature, we raised the polling rates way through the roof without properly compensating in the firmware. And we're going to get to that, but first I want to talk about another thing. Because if you remember from our chart, we had two different types of switches in this series, the microload switch and the general purpose switch. They went with the general purpose switch, but what's that other switch that we haven't talked about? Because it looks like even though it doesn't really meet the micro specs we're talking about, it would be a lot closer than 100 milliamps, 100 times closer in fact. Well, that will be the D2F01, also known as the Japanese Omrons. The problem is, for marketing purposes, there's no such thing as a 50 million bazillion D-jillion D operations version of that switch, although some manufacturers have stepped up and tried to one-up them with their own numbers that'll take 3.5 years to test. And also notice that says mechanical, not electrical, and electrical is what Omron is claiming in their data sheets. And I'm not busting on Kaiwa. I just bought a whole freaking bag of Kaiwa switches from Novel Keys, so, you know, I'm a fan, but that's kind of a dick move. Shout out to Novel Keys, by the way. But back to Omron, it should be telling you can't find the D2FCs anywhere except for like Newegg and, you know, gaming related places, whereas anywhere that sells any kind of parts that have any kind of critical tolerance will sell the Japanese version all over the place. And in fact, you could just get them right from Mouser or DigiKey, which is the simplest thing in the world, and I have. Now, I'm in no way saying that you're going to get 50 million cycles out of these Japanese Omrons, but I am saying that they are made specifically for this type of load application. So that means let's go ahead and look at what the difference is between the general switch and the microload switches, which means we have to do a material science section. Now, I chased this all around the internet trying to find out exactly what was used in the switches so I could be very specific, and they just say things like silver alloy and copper, and that's the kind of thing that really just pisses me off. So if I can show you like 3 different levels of detail in terms of data sheets, a crap detail might be like it's made of like copper leaf with a copper base and silver contacts. Then like a typical level might be, oh, it's a brass base with a copper alloy plate and silver alloy contacts. And then you have the good ones where they're like, oh, that's made of C2680, C1720, and AuNi10 alloy. You can see an example of that here in this fantastic data sheet from Panasonic switches, where they give you the standard version, the long life version, and break that down into each of the categories, showing you the operating force and all of the alloys involved in every one of them, with notes to see pages where they further explain that, as well as the applicable current range for each of them. Then further on, they show you each of those compositions of alloys in the contacts and give you the part numbers for each of the pieces, and that's wonderful. So again, angry me has to go and try to track this stuff down. So first, let's talk about silver alloy in quotes and what kind of plating in quotes that means. Now, the plating you're probably thinking about is like this connector right here, where you have silver plating, it's tin coated on the end, and then there's a gold contact on the front. That's called electroplating. Also like the electroplated gold contacts in this Panasonic switch. The D2FC series consists of one single plate that acts as both the spring and the contact, and that sits in 2 permanent contacts and 1 moving contact on this plate that's embedded in a plastic base. And as you can see, that doesn't look like it's plated with anything. It actually just looks like a weird, discolored, rusty looking metal of some sort. Well, for the purpose of this experiment, I busted out a couple different pieces of metal and a torch, one being a copper bronze alloy and the other being brass. And when I heat it up, you can see that kind of rainbow discoloration that we see there on the Omron switch, but it's tough to see, so now it's time to bust out the microscope. So I went ahead and I lopped the contact off and I dropped it under the microscope so you could see that kind of rainbow pattern. Now, I don't know if this is a result of treatment from the selective chemical deposition or from hardening or some other such thing. There's definitely some kind of coating on this, and it looks like a copper alloy of some sort, probably brass or bronze. And you can see right here, this is the point where this contact hits the switch plate, and you've seen the little flattened mark. But that's the off position, and it's not crucial. The on position is on the other side. So if I go ahead and I flip this over, you can see that this little knife edge here with the coloration on it, that right there where you see that mark is where the clicker plate smacks against it. It's kind of a cheapo way of doing things, and I'll explain why in a bit. But basically you have to coat copper in something, even copper alloys of most types, because otherwise it's going to corrode just like an old penny, or on the contacts of the ROM cartridges for your Nintendo that they cheaped out on and decided not to plate with anything. And they claim that there's a silver alloy coating somewhere on these contacts, and I just haven't seen it, so let's take the microscope and go in a little bit further. Looking at the first permanent contact, we can see more of that coloration there, but if you look right here where the plate sits, it does look like there is some kind of silver deposition in there, even though it's not what you might traditionally think of as silver plated. Same thing goes for the second permanent contact right here. Looking at the off position of the clicker plate, you can definitely see the imprint from where it was hitting the arm. And there's no silver here, it's not coated, it looks like it's probably just like phosphor bronze or beryllium copper, something like that. Looking at where that makes permanent contact, there's definitely no silver plating along this side, but here is the on position contact, and you can see the little divot where it's hitting, actually hitting disturbingly off center, but that's another subject. And this is a separate rivet that's probably induction brazed on here, and it definitely looks like it is coated with something or another. However, these contacts deform pretty easily, especially since they're off center a little bit where they strike on the plate because of the cheaper construction. And once you smash through that initial coating, you're just going to be doing whatever it is, probably some kind of brass or bronze, contact against whatever this material is down here that's obviously hardened and sharpened to an edge so that it'll make decent contact. And that's the same mechanism that's shared across the entire F2C series, whether it's the 3 million cycles, 5 million cycles, 10, 20, whatever. I actually took apart one of the 10 million ones on the left, this is one of the early ones, and one of the regular, office issue 3 million ones to see what the difference is. And really the only thing I could find was the 3 millions have this little notch in the edge of the plates, and I took a couple apart and they all sort of look like that, so it's probably some sort of marking. But the 20M marked ones have that mark as well, and I'll show you that later on, so I'm not really sure. But the construction, the alloy, and the treatment of the permanent contacts on the base were all absolutely identical, but the tolerance and the quality of the actual contact rivet seemed to be slightly higher with the 10 million cycle, so maybe that's the only difference that they do. And I imagine for like the 20 million to 50 million, they improve that rivet even more, and they probably give you different materials for the spring clicker plate. But the tension and the shape of the plates themselves was identical. Visually, the metals were identical, and they were exact same thickness at 0.6 millimeters. So it seems like across those different models in the series that are just rated for longer life, they may have a slightly different rivet, slightly different spring material, and then they're likely binned by resistivity measurements, force requirements, like how hard it is to push down the button, how much button pre-travel there is, and the actuation distance. And if you don't know what binning is, get off my lawn. Speaking of binning, there was a rumor that I want to set to rest right now, and that's that the Japanese Omrons are binned versions of the Chinese Omrons, just with higher quality control. They are absolutely not. They are entirely a different switch. The Japanese Omrons are a multiple part design. The leaf spring material and the return spring are two different types of materials and are a separate piece, and they have rivets and contacts on both the on and the off position. So you can see that return spring separate piece right here. And you can see that the contacts are all gold plated, like electroplated, not just selective chemical deposition. And then they have the brass rivet right here that is exactly the same materials and hardness as the permanent contacts right here for both the on and the off position. And really, I can see where the confusion is, because all they really say in the data sheet is like, it's rated for 1 milliamp and it uses gold alloy contacts. Now, I'm going to use these Japanese Omrons here as an example for a while because A, they're still Omron, so people are familiar with them and you can get them everywhere, and B, I think they're a great deal for what they are. I mean, if you get them in quantities, they're like 85, 86 cents a piece, but even if you get them from somewhere, you know, like Amazon or DigiKey or someplace like that, you can get 4 of them for like $6.26, and that's just $1.57 a piece, which means they're not all that much more expensive than, you know, the 50 million cycle regular Omron switches, the basic switches. And they're a lot cheaper than the high-end stuff like some of these Panasonics that go for like, you know, $3 a piece or more, which I do own and I will be happy to take apart on camera if you'd like. So let's talk about the difference in construction between these different types of switches and why it matters under different conditions. And this just doesn't apply to mice, this applies to everything, but there's this kind of sweet zone right around here in this circle where it doesn't matter what you switch with so much. You could practically use 2 bent paper clips in your finger and you'd be fine. You're not pushing enough current and voltage that you have to worry about using heavier duty materials to deal with arcing and carbonizing the contacts, and you're also not small enough that you have to worry about using noble metals in order to get decent contact. But once you stray away from that, you have to specify the materials for the particular use if you want to get A, reliability during the usable life cycle, and B, an extended life cycle. And that really just comes down to, well, science. There's no way of getting around the physical principles of the materials that you're working with. Right here we have the strength plotted on the left on the vertical axis and the conductivity, electrical conductivity, plotted down at the bottom. As you can see from the kind of arrangement of these materials, as you get stronger you get less conductive and vice versa. So for example, pure copper down here is very conductive, but it's not very strong. If you want something strong, you move up here to where you have like beryllium coppers and brasses, but you gain strength and lose conductivity, and then up here you have like silicon, copper, nickel type. Now this type of switch is a Z-type snap switch. Usually they're called a snap switch or a cherry switch or a limit switch, something like that. And they have 2 fixed contacts. They're calling one the hook here and the fixed end, and then the snap plate, which is on the top, and a compression spring on the bottom, as well as the contact. So as you apply increasing force to the top plate, that eventually reaches a point in the equilibrium between that and a compression spring with respect to the fulcrum in the middle, and there's a snapping action as it flicks very quickly to a different shape, and then the contact smacks against one of the either the on or the off positions. So the shape, the thickness, the mass, the material properties, and the size of the gap are going to affect how this switch feels, how much force you have to apply, how hard the click is, things like that. In conjunction with the spring on the bottom, that's going to affect both that and the return force. And then you have the contact on the end, which is the part that's doing the actual switching. And as we said before, the electrical properties versus mechanical properties are kind of set by the material and the alloy that you use. Something like stainless steel has very, very low conductivity, but very high strength, whereas spring brass would have very high conductivity and much, much lower strength than stainless steel. So first, like general switches like the D2FC F series from Omron, you have your top plate, which is the clicky part, and then your spring on the bottom and your contact at the end is going to make your electrical contact. Then you have your plastic body here with your stamping that's going to be, I'll just call it the base plate, and then right here you have your on and your off contacts. And electricity has to flow through that to make a circuit from this top plate here, which has to be made out of a springy, resilient material so you don't get mechanical failures. Your spring has to be made out of something that's very resilient, and then your contact has to be more conductive, which is why they plate that with some kind of silver alloy, as well as these pivot points right here, where the little pivots or the fulcrums on the plate are going to be. And then in order to not wear down this brass plate, they hardness treat this bottom clacker plate so that you don't wear it out very quickly by deforming the material. And it's a good way to make an economical switch that still works fairly decently under a wide range of circumstances. The name of the game for these is compromise. By using just a single base material and then treating it for hardness and for conductivity, as well as using just one type of material for the spring plate for both the top clicker and the bottom return spring, and then just adding a braze on with more conductive material in one place for just the on position, you manage to make a switch that's decent across a wide range of conditions. It's very mechanically rugged because there are very few moving parts. You've economized your materials and made it very simple to put together, which also contributes to it being more affordable. And you have very few points of mechanical failure, so you can say, yes, we're going to get 20, 30, 50 million cycles out of this mechanically, but you are compromising on it electrically, and you're limiting the range that you're able to use it effectively in electrically, particularly when you get down to very small voltages and currents, because you're not optimizing these particular materials for those conditions. Hence, general switch. They are generally applicable and generally good across a range of typical values. As long as you stay within those, they're wonderful, with the added benefit of being A, cheap as dirt, and B, very easy to repair if something goes wrong. Now let's contrast that with purpose-built microload switches. You have a separate top click plate, and then on the bottom you have a separate return spring. So theoretically, if you do it right, you can make those out of different materials and optimize the properties each, one for feel and one for return. Then you have your rivet that you can optimize for electrical conductivity, as well as your base plate that's electroplated with a noble metal for higher life, lower corrosion, and better conduction. And then you have your rivets on the on and the off positions here that are made of a separate material that's stamped into the base plate, and that's the same material with the same hardness as your rivet on your click plate on the top, and that's going to be made out of materials that are specifically built to switch the loads that we're talking about. So in the case of the Japanese Omrons, that's probably going to be a copper material with probably nickel plating and then gold on top of that, or a gold alloy. And then in one of like the super fancy schmancy switches, it'll switch down to like, you know, the tiny little microamps ranges. It'll probably copper alloy with a nickel coating on top of that, a nickel palladium coating on top of that, and then you'll have probably a gold alloy or pure gold with some kind of embedded nanoparticles or oxides. Usually that's going to be aluminum or platinum. And those will be used for critical switching of very low logic level, low current loads, like medical use or critical devices like the airbags in your car or something like that. And the reason for using those different types of metals and different layers of metals is, of course, because of, you know, material science. Like we said, as you get more conductive, you're softer, and you have to pull dirty tricks to kind of keep the top metals from deforming. You have to make sure that if it's gold contact, it's gold touching gold, and they're the same hardness so they don't wear each other out or rub it off. Then underneath that, you need something that's also conductive and hard and will help that material stick to the copper material without altering the properties of each of those by electron migration and things like that. So as a comparison for how that works, there's this chart right here. Moving from left to right, you can see the hardness across the bottom and then the layer structure above that. All the way to the left is our typical generic component like maybe the leads of a resistor or something like that. It'll be copper alloy with like nickel and tin on top of that, or maybe just tin on top of copper alloy if it's really cheap. It's not very hard and it's not particularly electrically conductive, but it's easy to do and cheap. And that's what you might find in like your general basic generic switches that you'll find in like office mice and things like that from like Dell and Hewlett-Packard. Then we have the land of the Chinese Omrons, which is regular copper alloy with a silver alloy on top of that, which is both a bit harder and much more electrically conductive, followed up by where the Japanese Omron switches would fit, which is like a copper alloy with nickel on top of that, and then a gold alloy on top of that, also called hard gold. And then the super fancy schmancy stuff that is like 4 or 5 times harder than the construction that's in our general switches, like the Chinese Omrons, where you have optimized materials like copper alloy, nickel on top of that, palladium nickel on top of that, and a thin layer of hard gold on top of that. Now, if you remember back to where I compared the 10 million and the 3 million cycle Omrons against each other, they seem to be almost identical in construction and materials on the inside, save for a couple things like the rivet and the characteristics, the physical characteristics of the plate themselves. So I suspect that most of what's happening as we move up to the higher cycle life ones is they're using slightly different materials for the spring plate, as well as using slightly different materials to coat the contact with. But they don't give specifics. They just want you to kind of take their word for it. And the problem with that is, even when you're talking about just saying gold alloy or silver alloy, we're talking about a whole bunch of different alloys. Now, these are the typical ones that are used, AgNi10 through AgNi30, depending on the content of silver, which affects the strength, the hardness, and the electrical conductivity as a trade-off of each other. Now, in some of Omron's data, they do specify, like with this relay here, where they say it's AgNi10, which is the softest but most conductive. But like I said, I suspect that varies from cycle life switch to cycle life switch, and that falls right here in this general category as far as the contact surface chart that I showed. And the problem that I have had in 100% of these switches is that eventually that contact deforms by clacking against this hard bottom plate. And then you start to lose conductivity, and the position shifts a little bit when you're pressing it. So you get the double click issue, and then you get the click and drag issue. To make that problem even worse, the clicker plate strikes off center slightly, so you are chattering to the left and the right as you apply pressure to that, just because it's not perfectly even and hitting in the middle. That's just like having a seesaw with one side drastically longer than the other one. And very quickly, as that switch wears out, it'll tend to skid off to the side, and you get this long scraping contact path, which will give you double and triple click issues. Here's an example of one of these exposed. If you click right in the middle, it's a very nice click. But if you go ever so slightly to the left, you lose that. And then if you go more to the right, where it's more off-center, you don't get any click at all. You can just see the scraping, twisting action. That could be made worse by your mouse design. This is probably hard to see, but you can see at halfway depressed, this switch does have lateral play back and forth. Now, that could be eliminated completely by perfect mouse design, and a lot of these mice are pretty good, although still not perfect. But some mice are kind of junky in that category, like this mouse that Microsoft has the balls to charge $50 for. You can see how flexible this plate is, and that's definitely going to let you press the switch off center, which is super crappy. But this is from the company that's trying to charge $200 for a non-hobbled version of their operating system, when all their competitors are literally giving away their operating systems for free, literally all of them. But this isn't a dump on Microsoft session, so I'll let that go. But back to the switches. None of this is a secret. None of this is obscure. This is all very well known to all parts of various different industries since, like I said, 1934 or so, when they started working with these switches, and even before that. Quote Tony Kufalt, the author of many electronic textbooks, normally a switch's wetting rating is far below its maximum current rating and well below its normal operating current load in a properly designed system. However, there are applications where mechanical switch contact may be required to routinely handle currents below normal wetting current limits. For example, if a mechanical selector switch needs to open or close in a digital logic or analog electronic circuit where the current value is extremely small. In these applications, it is highly recommended a gold-plated switch contact be specified. Gold is a metal that does not corrode as other metals will. Such contacts will have extremely low current requirements as a result. Normal silver or copper alloy contacts will not provide reliable operation if used in such low current service! So to sum up, for microloads, silver bad, gold good if you do it right. So that brings us to the problem of wear. Now obviously all these noble metals, the more noble you go, the more soft they tend to be. So ideally you want them to be the same hardness, to have the same grain, and be exactly the same material or alloy. Otherwise we're just going to be CSGOing the lifespan of our mice down to a few months. And the mechanics behind how that works are very well known, and I won't reiterate them here. But to refresh on our Chinese Omron switches, we have our treated base plate that's hardened and sharpened to a point to make contact with our rivet that's brazed onto our spring copper plate, and our off contact that doesn't have any kind of coating on it at all, but with the permanent contacts with a slight coating of silver alloy. And that contrasts with the Japanese Omrons that have a separate rivet that is copper coated with probably a nickel substrate that's coated in gold, and that's for both the part that's on the clacker plate and the rivet that's embedded in the electroplated base plates, with that gold alloy contact hopefully being the same hardness on both the rivet that's on the clacker plate as well as the rivet that's on the stationary contacts. And then it uses a separate spring like you see on the bottom here, as opposed to unifying it as one piece like on the top. And then the bottom compression spring or return spring, whatever you want to call it, is made out of a separate material. Now let's talk about our little gold plated rivet right here, because the geometry is very important as well. Let's switch back to the Chinese contacts right here. So you can see as you're depressing that, there's a scraping action back and forth across the stationary contact as you overpress. Now, under normal circumstances, that's not a bad thing. There's a thing called contact wiping, where those contacts are supposed to slightly rub against each other to free the surface of any like oxide coatings. The problem is when you have dissimilar surfaces, or one surface that's smooth and coated and another surface that's rough, you're just going to be grinding down one of those two surfaces and lowering your life and making intermittent chatter. Whereas if those surfaces are the same hardness and you put some thought into the geometry of it, so they do a little bit of a roll as opposed to a scrape, then you're just cleaning them and not wearing them down. So scraping wear equals bad, especially with unequal metals, but wiping clean equals good, especially with equal metals or equal hardness metals, or the same metal preferably. And since we're talking about switching in hardness, now I want to touch on bounce and chatter a little bit so you know what the issue is here, and this is going to tie into polling rate. Yeah, you almost thought I forgot about that, didn't you? Now, technically, switch bounce is after you switch the voltage, you have a period where it's unstable, where you have contact, no contact, contact, no contact. And you have to deal with that either mechanically or in the software, because otherwise you're going to be registering mouse clicks during that whole time. So basically the way that you deal with it is you want your computer to ignore anything that happens in the period between these two vertical dashed lines, because you know that's just going to be schmutz in there. But you don't want that zone to extend too far and for it to ignore your next mouse click, because obviously that's bad. Now, unfortunately, that spec is usually not in the datasheet. Usually, sometimes it is. But the problem is that bounce is dynamic, as in it's not a fixed value across the entire life of the switch, and it varies from switch to switch, dependent on where, how you're using it, the design of the switch mechanics, as in like, you know, what type of kinematics it's using and what materials it uses for like the spring and the return plates, and the damping properties of the materials themselves. As in, if you bounce a billiard ball off of a concrete floor, it's going to bounce very high, whereas if you throw a beanbag at a concrete floor, it's just going to because of the rebound damping properties of the beanbag. And yes, I said damping and not dampening, you Philistines. Now, typically, that's going to be in the hundreds of microseconds to several milliseconds, and it also increases with wear. It increases with the hardness of the contacts, and it increases with the fast rate of return of particular types of springs, like stiffer springs or more resilient springs, and with usage, as in the bounce period is longer with fast repeated clicks than it is with just single clicks. And back in the day, or with simple switches, that could be handled with like a hardware solution where you're just increasing the time constant by adding a capacitor across the contacts. It takes a certain amount of time to charge up to a level where it triggers the logic voltage. Typically that's debounced in the firmware, and depending on whether that's set by the manufacturer or whether that's changed by the, the second party that's going to be using it, it's usually in like the tens of milliseconds, even down to the singles milliseconds. For example, I looked at the datasheet of an Analog Devices dedicated debouncer IC, and that's adjustable anywhere from 4 milliseconds all the way on up, with the default being around like 6 milliseconds. And again, what that does is it waits for a signal, then it says, hey, there's a click, don't do anything for a certain amount of milliseconds. Okay, now we're good, let's look for another click. And hopefully that period is good enough that it cuts out all this schmutz, and then it's still ready for your next click when you're about to do that. So let me get to polling rate wheel click, and then we'll talk about how that relates to bouncing. So essentially your USB bus has to poll or ask your mouse hardware every so often if there's a click. Like it's saying, hey, is there a click? No. Hey, is there a click? No. Hey, is there a click? No. Yes, there's a click right now. And how frequently it does that is called the polling rate. And that's measured in hertz or cycles per second. And you can convert hertz to milliseconds very easily. And what that polling rate is controlled in your software that tells your hardware how often to check for a click. And that'll vary from one mouse or peripheral to another depending on what the hardware is capable of. Now, faster polling rate means that it's going to be asking it much more often, so you're less likely to have to click and then wait several milliseconds or whatever until the action appears on your screen. And I won't talk about how that's affected by vertical sync and frame buffers and the frame rate of your particular monitor and the response time, because that's a whole other freaking can of worms that I don't want to get into here, even though that is all interrelated and it does matter too, to a certain extent. Now, older peripherals tend to have a slower polling rate for a couple reasons. One, gaming wasn't a thing back then, so rapid clicking wasn't a consideration, and a lot of these older peripherals had an extremely long bounce time. Like old keyboards, you may have had to drop the polling rate all the way down to 60 or 80 hertz or something like that, otherwise they would register double click. Oh, and consequently, this doesn't apply to PS2 bus. That used an interrupt-based system, not a polling cyclic system, so that's a different ball of wax altogether. Again, another can of worms I'm not going to get into here. And that bled into the early gaming mice, where a lot of these were locked to 125 hertz in the software, even if they were capable of faster rates. An example would be the MX518 that was locked by software to 125 hertz, even though the hardware was capable of 250 or 500 hertz, or maybe even higher. It depends on the generation of the chip that's used in there, because they went through a couple different iterations. But the software used at the time was the Logitech setpoint software that was set at 125 hertz, except for some of the later versions I think you could actually change it, but on a driver level those were locked to 125. Now, how does that tie into bouncing? Well, 125 hertz converted to milliseconds is 8 milliseconds. So you're only going to be registering a click every 8 milliseconds. Because whether the switch is bouncing or clicking or jumping through hoops or whatever the heck it's doing, your computer doesn't matter because it's not asking for a click. So any of this schmutz that happens between that period is not going to register anyway because your computer just isn't asking for it. So that just means that you get virtual debouncing of about 8 milliseconds because you're just not getting a signal. Now, I know it's not exactly 8 milliseconds because you could be clicking somewhere in between those window times, but maximum 8 milliseconds. But because of demand from gamers, polling rate gets much faster these days. Like my G502 goes up to 1000 hertz, which is 1 millisecond of time. So whereas this window where it's not getting any signal may have been much bigger before at 125 hertz, it's now 8 times smaller, so we probably could be picking up some of that schmutz that we wouldn't have before with the slower polling rate. And again, I realize there's overlap and you could be clicking anywhere in that window, but it is definitely have the higher probability of it being worse with a higher polling rate. There's also the additional issue, which isn't as big a deal, but these older 8-bit chips worked off of a much slower clock speed, usually around 16 megahertz or something like that, whereas the faster 32-bit chips like these may be 5, 10, 20, 50 times faster than that, and the rate that you can send a signal to that and have it processed is much faster on those than it would have been in an old chip, so you have that a little bit of extra buffer from just the overhead of the operations and the rate at which the chip can poll its interrupt if you're using an ISR for your debounce routine, which means you're additionally sending more windows for the possibility of picking up switch bounce or chatter. And this does happen, as we can see with the double click problem that I showed earlier and the click and drag problem when you're trying to, drag across somewhere. And that's the reason that some people have found that if they uninstall the Logitech software and they install Microsoft software instead, the IntelliPoint software or whatever it's called, they're getting rid of some of that double click problem because they're lowering the polling rate, which gives you a larger possible window of 8 milliseconds of quote ghetto debouncing. It's not really a debounce routine. It's just that you're not going to be reading those signals, so it doesn't matter if it's bouncing. Now, obviously, that works better for the double click problem than the click and drag problem, although they are related. But the click and drag problem is more with variable pressure and an intermittent signal. I like to call that chatter. And I said chatter, so let's talk about intermittent signals. Because bounce is one possible problem that you're having when you talk about double clicking, but click and drag is definitely intermittent signal, and double clicking can also be intermittent signal. Remember, on our Chinese Omrons, we're hitting this little clicker plate kind of off center and scraping the living crap of it against the bottom plate, just like this right here. So we're getting excessive wear on the contact. And as you're dragging back and forth those dissimilar materials, you're getting signals triggering one after another as you're making contact and losing contact and making contact and losing contact. And obviously that's going to be picked up with the faster polling rate on your mouse. Now, this could be fixed by the manufacturer in the firmware somewhat, but apparently it isn't. There's got to be some kind of debounce routine in there. However, it's closed source firmware, so I have no idea what it is. That's one of the reasons I'm a proponent of open source, because we could have possibly fixed this years ago. And that's also tied into the construction of the switch. Obviously, these Japanese types with gold-plated contacts and the much larger contact area, as well as the much slighter rubbing action against two metals that are the same hardness, as long as you don't wear out those noble metals, is much preferable than the clicker plate with just this one contact is rubbing against the hardened dissimilar material that, as you can see, is very, very rough. And really the only thing that's making it continue to make contact is that this contact is deforming, which is both bad and good. It's bad because we're wearing it out, but it's good because it will continue working. This could be made worse, actually, if you make the moving contact harder, which presumably is what they're doing on like the 20 and the 50 million cycles, and you're going to get additional bounce and chatter much earlier in the life of the mouse, which the PWG users with the Omron 50 million cycle switches have discovered. They're getting problems after a couple months instead of after a couple years. And that also all goes to show why mice like the MX518 have kind of gotten this godlike status for being bomb-proof. Because as we showed, they're running a higher logic voltage, they're running higher current through the switch, they're using the cheaper switches, they're running at a lower polling rate, and they have a much longer debounce time. So even if the switches are as worn out as they are in a couple-month-old Logitech Pro, they're probably still going to be chugging along. Which, as you can see by how much wear there is on my mouse, this thing still freaking works perfectly, although it doesn't work up to modern specs, as in fast polling rates. But I guarantee you these switches are worn to crap. Actually, I'm going to pause this video right now and I'm going to take this mouse apart on camera and I'm going to look at the left click switch underneath a microscope and I'm going to show you. That way you'll know that the whole polling debouncing thing is true. The things that I do for you people. Now, I shot this all in one continuous shot so you know there was no foolery going on here, but I'm going to have to fast forward through parts of it because it's 16.5 minutes long and I don't want to waste that much time in this video. It's already an hour long at this point as it is. And then I overlaid the microscope footage on top of this so you can see what's going on while I'm fiddling around on the desk. So right here, I'm just taking apart the body and I'm going to pull this switch out. So as you can see right here, after I get this off of here, this is one of the regular 20 million cycle guys. If I can get the camera to focus in on that. See 20M at the end. And I can already see right here that this contact plate is super worn out. I don't know if you'll be able to see it on camera, but you'll be able to see it when I put it under the scope. Man, someone is having a full-on girlfriend meltdown in 2 languages outside my window. Hang on, I'm going to put the microphone over there so you can hear it. Good times, life in the city. Anyway, let's fast forward through this scope setup. All right, I hit record on the scope right about here. Or here, and there we go. So now you're going to see on the left side, this is what's obviously the view from the scope, and on the right side is me fiddling around with things. First thing we're going to look at is the spring contact, which is super worn out. So right here is the spring plate. As I zoom in here, and let me splice in a zoomed in picture of the off position of the plate. And you can see how super duper worn out that is. Now, flipping it over and looking at the on position braze on, look at all that wear. And you can see on the spring, on the bottom part of the spring there, how bent the one side is. That's because it, it doesn't hit in the center and it twists that spring. So this has a lot of fatigue on it, even though it's still functioning. This is going to fail mechanically fairly soon, probably, in quotes. I'm going to fast forward through readjusting so we can look at the stationary contacts right here. And you can see, just like the other one, if I can get this stupid thing centered, right there, we have the silver cladding on the permanent contact. More fast forward, and now we can take a look at the on position plate. You can see all that wear there on the on position plate that's actually on the body of the switch. And then I'll go ahead and give you an extreme close-up view of the spring plate, the off-position terminal, and the wear that's on there. It's worn and bent. That's how much this has been used. And that's not finger pressures going against that. That's just the pressure of the plate clacking up against that contact. And then if I move it over a little bit, you can see that part of the spring plate that's kind of worn and creased right there. And then I'll slide down a little bit so you can see the pivot, the permanent pivot point of the spring right here, which is also super duper worn out. Then I'll fast forward to focusing process, but you can see the absolutely redonkulous amount of wear that's on this, the on contact bottom part. See that little wedge cut out of the right side there from grinding against that permanent contact plate. Now I'm going to uber fast forward through putting this stupid thing back together, and I'm shooting this a little inside info first thing in the morning. I'm hopped up on coffee right now, and my hands are super shaky, so it was an extra pain in the butt to get that stupid thing back together. I had to take it apart once because I had a hand spasm as I clicked the top plate on, and it didn't go down right. And it occurred to me right here that you can't see me clicking the mouse and the test on the screen at the same time because I'm running a capture on the stupid camera, and I can't do a desktop capture at the same time. So I'm just going to take this camera and tilt it up, and then you can see right here the results of the tests. Still working. But that's all just to go to show that, but that's not even English, that no matter how mangled that switch is, well, not no matter, but even though that switch is much more mangled than would be working in my G502 or some of the other modern mice, after all, on the right is what the switch on my G502 looked like when it stopped working, and on the left is a switch on my MX518, and that is still working, and ostensibly these are the same switch. Because of the way that electrically it's running and because of the software that's involved, the polling rate and all that type of thing, it's still functioning after all of these years despite being super duper ragged inside. And I guarantee you that both of those switches are way more worn out than the switches that fail after a couple months in the PWG, Pro mouse. So where does that leave us? What does that tell us? Well, as the end user is stuck in a situation, we got a couple options. We can take them out and put the Japanese switches in there or something similar, but these aren't rated at gaming specifications anyway. They're just rated for the electrical loads, so they do have 3 times or more the electrical life of the regular D2F models, but that doesn't necessarily mean that they're going to hold up better under being mashed. As a ghetto fix, you can also change the polling rate in your driver software. That may be a quick fix or a temporary fix until you can, do something else about it. But you're still going to have the quick debouncing that's not adjusted. So you could do what other people have done and install like the IntelliPoint or SetPoint software that's going to lock it to 125 hertz and give you a longer debounce time. But again, that's just a kludge and a temporary fix, and you're losing performance in the deal. I mean, if you're going to cripple your gaming mouse, you might as well just use a high-life office mouse or something like that. You could take it apart and clean them up and lubricate them with something like Fader Lube or Deoxit, and then retension the return springs so that it's going to make better contact with it. That'll help for a little bit, as long as you don't ruin the switch when you're taking it apart. Or you could go ahead and try the Japanese Omrons and see how they work out for you. They're not that expensive. Or gasp, horror of all horrors, try a different brand of switch. Maybe one that doesn't use the 2-spring design of the Japanese switches, but does use a rivet on it that's going to give you better electrical contact at micro loads. Although, as we know, all these different brands of switches have different feels, and the Omron switches have a very light feel. But I did set up a test jig with some high-wind linear rail and a gram scale, and I put various models of both the standard Chinese Omrons and the Japanese Omrons on it, and they do actuate right around the same force. The Japanese were much more consistent around like the low 60 grams, whereas the Chinese ones could be anywhere from like the mid 50s to the high 60s, so they both have about the same feel. But you could just go ahead and swap it out for the same switch after it wears out. But if it's because of electrical conditions within the mouse that are not letting the switch live its proper lifespan, then you're only going to get a couple months of life out of these after all. So switching from like the 50 million cycle ones back to the 20 million or the 10 million or even the 5 or 3s might do better for you. There's also other electrical kludges and workarounds that you could do. You could add a debounce circuit to it, which again is going to limit your click rate. You could also do an old industry trick and bypass the switch with a very small value capacitor like 0.1 microfarads, and that'll help kick a spark that'll let it break through the wetting current, although again this is just another kludge. And while we're adding electrical components, you could just add another resistor in parallel with your internal resistor, pulling it up to, your voltage rail. That's going to bring the current through the switch to like a milliamp or more, and that would definitely give it longer life, but at the risk of frying your microcontroller if you do it wrong. But all in all, it comes down to the manufacturers of both the switches and the mice to deal with this. The answers would be making switches better for gaming conditions, not just taking existing conditions that are popular because of hype and like adding bells and whistles to them to give them longer cycle life, which actually is resulting in shorter cycle life. Another possibility is just smarter firmware. I mean, if you're having hardware problems, you can adjust a whole lot in your firmware, and while I do think they should fix the hardware problems anyway, there's no reason you can't rewrite your debounce routine to compensate for it a little bit and to compensate for the aging of the switch. So when they're nice and fresh and new, you can have a lower time, and when they're getting older, you can extend that debounce time a little bit more. Furthermore, if you're really smart, you could program it so that it detects if you're clicking and dragging and then really lengthens the time. And then if you're fast clicking, it could also change to another algorithm so that it's going to extend the bounce period there as well. And you can even make that adjustable on a user basis. So smart features are great and all, but we vary as humans, we vary in play style, so there's no reason you can't just add another tab to your gaming software and make all of those parameters adjustable within a range. Double click problem, push this slider until it goes away. That's not going to fix everything, and it's definitely not going to fix bad hardware design, but it'll help a bit. Also, a couple fixes that I would personally do if I were a mouse manufacturer is I would redesign the mouse circuit. Yet ain't broke, don't fix it thing doesn't work anymore because it's definitely broke now. So if the problem is we're not pulling enough voltage, enough current through there, pull more voltage and current through there. It's just that simple. All you have to do is add one resistor to each of the buttons. That's fractions of a penny, and I think you could argue with the bean counters that it's a worthwhile expenditure. And you could always use a plug-in switch interface so that if people are married to a particular switch that they know is not going to have a terribly long life, then you could always just make the design of the mouse so that there's a panel that slides out under the button or a removable button, and you could just hot swap in a new switch and you're good to go. Mechanical gaming keyboards have been doing this, well, forever. Now, I understand that most people buy new mice because the switches wear out and things like that, but as I will get into later on in this video in a little bit, you can spin that into actually getting more money out of the customers and make them happy at the same time, which is amazing. Everybody wins. Funny how that works. But basically I'm saying fix the parts that are spec'd, fix the body design, fix the electronics, and fix the firmware. But basically what you're saying is redesign the entire mouse, which means not using the same boilerplate circuit and just adding bells and whistles and marketing stuff, speccing the proper switches, and then making the appropriate changes in your firmware. And if you're unwilling to do a redesign like that and give the customers what they want, you have to have a hard look at yourself in the mirror and say, do we suck? We're cranking out designs and selling for $150 with hype switches, and they're breaking even though we're claiming 50 million clicks and they only last like 6 months or so. Does that mean, are we the baddies? I don't want to crap on any manufacturers here, and I've been using their stuff for years, but if you're tripling the price of these things and the bean counters are not letting you do a redesign and add one single resistor to each switch because a fraction of a penny of cost, customers would then have every right to be skeptical about anything you say in the future. So let me sum this up and then offer my own suggestions. And bear in mind, I'm not an electrical engineer. I'm just a guitar player who's a little bit too clever for his own good and isn't afraid to get his hands dirty with the details of these projects. So I'm sure these companies can have no problem handling it. So we've essentially just reached the point where feature creep and the desire to ride out hype for certain components has overridden the ability to keep up in an engineering sense. Now, it doesn't have to be that way. You can re-engineer and make things solid and test them properly before you release a product. And my mind is actually blown that nobody saw the warning signs here ahead of time. Nobody in the design department, or maybe they did and they were just ignored. If you did have an engineer that looked at the switch and said that this is not going to work very well, and the bean counters came in and said, we're not paying for a redesign and we're not paying for the cost of one more resistor per switch, that'll cost us fractions of a penny. How will we be able to stay solvent as a company? Then that's despicable. So you could keep the same Omron switches if you want, even though they're not properly spec'd, if you look back at the old stuff and say, all right, well, we have to compensate for a few things. We have much faster pull rates here, so we're going to have to adjust our debounce period accordingly. We're going to have to put some work into this and make it smart, make it dynamic, and make it adjustable so that it changes according to click and drag, fast click, slow click, the age of the switch, and other conditions involved. We're also going to have to redesign a circuit. We already have a 5-volt rail there. We don't have to run it directly off the internal pull-up resistors in a microcontroller. We can just add one resistor off the 5-volt rail and send that right into the microcontroller, making sure we draw like a milliamp of current through the switch or whatever it is that takes. We know we can do up to 8 or even 20 milliamps per GPIO, assuming we're not exceeding the total draw of the switch or the total draw of the microprocessor if you have like an 11 switch mouse or something like that. But you can figure that out. That's what you're paid to do. Another option would be, and this is the way that I mentioned before, you could make more money and make the customer happy at the same time, is to make the switches hot swappable. Like I said, they've been doing that with professional grade gaming mechanical keyboards for a long time, where you could just pull the keycap off, use a puller, yank out the switch, plug in another one, and you're good to go. That way, your WASD or arrow key switches that you're wearing the crap out of can just be replaced instead of having to replace the entire keyboard. And maybe that'll cost you money in the long run, but maybe it won't. If you continue to innovate and offer mice that have features that people want, they're going to buy them anyway. And even the people that hang on to their old mice, if they can know that they can replace the parts that are going to wear out very easily on their own in a user serviceable way, then they're going to feel more comfortable, A, buying your product, and B, you can sell them the switches. You can even sell them customizable switch packs with different press tensions, different engagement points, just like they do with mechanical keyboards where you have like clicky, non-clicky, tactile, linear, etc., etc. And there's no reason that you have to just ride off the hype of a particular switch. You can just say, hey, Omron or Kale or Panasonic or Honeywell or whoever, let's get together and make the perfect gaming switch. One that works at these levels but is still super durable mechanically. Maybe we should look at the designs that work, take the best parts of them and roll it into a new switch. And then that's a unique selling point right there. You could say, not only did we take that Omron switch that you all love, but we made it gaming grade. And you could actually be truthful about gaming grade, which is usually nonsense. If there were a mouse with all of those features, I would buy it in a minute. And eventually, this plague is going to start hitting all the other manufacturers as well. I haven't pulled apart their mice to see what they're doing in terms of the current, but I dare say that if we're running at the same clock speeds, the same interrupt speeds, the same high polling rates, and the same low currents and voltages, this is a plague that's going to be spreading to other manufacturers as well until somebody figures it out, and they're going to make the modern MX518 that's just a tank that lasts forever, and everyone's going to gravitate toward that. Either that or some jerk face like me, but with more money, is going to come along and make an open source mouse that's completely modular and has all the features that everybody wants, doesn't cost a bajillion bucks, and they're going to blow your entire business model out of the water. All right, that's the end of the video. Thank you very much for sticking around through this whole thing. I cut this down from 2.5 hours to an hour and a half, and then I cut it down again as much as I possibly could. I know I left out a lot of information, so if you have any questions, leave them in the comments and I'll try to get to some of them, but chances are I answered it with stuff that I cut out. If you're like, oh, you forgot about blah, 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 I didn't forget about blah, blah, blah. I just had to cut it out for time. And while I'm perfectly willing to tackle any software or hardware, no matter what it is, 3D printers, computers, whatever, this isn't my area of focus, so I'm going to try to tag a couple guys that do this for a living, like maybe Steve from Gamers Nexus, because he tends to get into like the technical details, or some of the other dudes, so hopefully they can pick up this baton and run with it and get you all some better mouse designs, because I just don't have any clout in that industry. And if you guys want to tag them with that as well, feel free to go ahead and they can get a hold of me. And as always with these videos, if you like the content, if you like the kind of stuff that I'm doing, I have support links down in the description below. I'm also going to put some affiliate links down there to a couple of the switches that I mentioned, so if you want to try them out, go ahead and do that. Buy them for a couple bucks and they'll kick me back a couple pennies a piece or something like that. I don't know that there's a switch that I necessarily endorse right now, and that's tough to do because, like I showed you, the conditions electrically within each of these mice are so different, but it doesn't cost a whole lot to experiment if you just know how to swap these in and out. And I did buy, in preparation for this video, a soldering and desoldering kit in case you don't have something like that. I tried to find the cheapest one I possibly could so that I could post it in the links below, in an affiliate link, and say, hey, if you don't have this, go ahead and grab this. It can only benefit you in the future. So anyway, until the next video, get out there and make something awesome. Or get out there and mod your mouse until it's awesome. See you later.